My name is Emma Snyder, and this is Lab 5 for Physics 2, Magnetic Braking and Faraday's Law. The purpose of this lab is to analyze the relationship between an induced current in a metal tube and how it impacts a magnet that is currently causing the tube causing the current in the tube by being dropped through it. The principles used were the Boy-Savart law, the definition of magnetic flux, Faraday's law, and Newton's second law. All of the equations for these are seen on the slide. And for a preview of the results, the average time that it took for the magnet to fall through the loop was 0.8 seconds. And in the model, it reported that the time was 0.938 seconds in order to fall through the loop, and the velocity graph is shown here. The initial conditions of the experiment, the bar magnet is outside of the tube and the velocity is 0. And then the system is the bar magnet and the surroundings of both the aluminum tube and the earth. So in this experiment, the magnet is dropped through the tube, which performs magnetic braking on it. And then the time that it takes for the magnet to come out the other side is measured, and the experiment is repeated to get an average time. This lab was modeled using this program that I wrote. Here, we are setting up the basic geometry of the aluminum tube. And then here, we started visualizing the bar magnet. Below that, we created a couple different just initial conditions and then set up the magnetic field function, which is right here. Then we calculated d flux dt. And then we iterated it in order to create this display of the magnet falling through the tube. Obviously, it's a little slowed down in comparison to what would happen in real life, but right here is the graph, and this tube showed, okay, and here's the time that I said earlier, 0.938 seconds, which is slightly off from what we found in the actual experimental model. So the model and the experimental data did not line up when it came to the amount of time. One was 0.8 seconds and the other one was 0.938 seconds. However, this wasn't a huge separation, so we don't really have to assume that any of the major parts of the experiment or the coding were done incorrectly. Likely it was due to difference in air resistance or in some form of maybe mismeasurement in the actual labeling of the tube, but the fact is that there is no air resistance in the model where there is air resistance in the actual world, so that may have made a difference. So as far as sources of error go, the major possible source of error is not starting the timer perfectly when the magnet is dropped or stopping it incorrectly when the magnet comes out at the other end of the tube. The precision would make a huge difference, especially when we're working with such a small margin of difference between the experiment and the model. Now we're moving on to the what if questions. So what if the resistivity of the conductor were reduced to 0 or as close to 0 as possible? And if the resistivity of the conductor was very close to 0, then the current would become very, very large. Because the R is in the denominator in this equation here, and that would lead to the magnet falling at a slower rate due to an increase in the current itself. And then what if there were holes or slots cut into the tube? The currents would be smaller because they wouldn't be able to travel all the way in circles every single time. There would be fewer of them as well. So therefore, the force upwards would be reduced, and the magnet would therefore fall through the tube faster and come out the other side in a shorter period of time. Thank you for watching.